In this video we're going to show that if we have an object of mass m attracted to a fixed point O under an inverse square law, then it will map out an elliptic orbit. So let the distance from m to O be that radius r, and let the angle that the object sweeps out as it goes round the orbit be the angle of theta, and there's a small displacement here, ds. So we can say that the force on the object is directly proportional to the mass and inversely proportional to the radius squared. So the constant of proportionality here will give a value of mu. And we can say through conservation of energy that the kinetic energy plus the potential energy is a constant. So we can use the idea of least action, in which we can say that 2 times the integral of the kinetic energy with respect to time is a value of I, which is stationary. So we've seen that in a previous video. So therefore we could say that 2 times the kinetic energy, which is going to be given by half mv squared by dt, take out the value of m, the 2's cancel, you have mv squared dt equals I. But we know that the instantaneous velocity is going to equal to the small displacement ds divided by small time change dt, the infinitesimal ds divided by infinitesimal dt. So therefore we can say that the vdt is going to be equal to ds. So we can put this here into this equation here. So it means that we're going to get rid of the one of the v's and also the dt, and we'll be left with the vds. So finally we can say that the equation we're looking for is m times integral of vds is equal to I, which is a stationary value. So now we've got to go ahead and find what v is, and we've got to find out what ds is. So we'll do that in the rest of the slides. So we're looking to find the values of our v and our ds. So we'll start off with our values of v. So we want v in terms of the radius r. So if you come up here and we see we want the velocity of a point here as it travels round in terms of the radius r. So at each point here the velocity will be different depending on the distance r to that point. So let's go ahead and we'll work these out. So we can work out the value of the velocity by looking at the potential energy and the kinetic energy. So we know the potential energy plus the kinetic energy is going to be a constant. So the kinetic energy is going to be half mv squared, and we can get the potential energy from the work energy theorem. So we can say that the change in the kinetic energy is going to be minus the change in the potential energy. Now we can see that if we think of it in terms of a pendulum. We've seen it whenever there's a pendulum, the kinetic energy plus potential energy was a constant, and all that happened was whenever the pendulum moved, whenever the kinetic energy decreased, the potential energy increased, and vice versa. So if we were then to go ahead and we write the change in kinetic energy, which is the work, it's done as the force times the distance, but in this case here the force we have is actually a variable force. So the variable force is given by our mu upon r squared, which really is the force due to gravity. Newton's force due to gravity is given by our m1 m2 times the gravitational constant upon r squared. So that's really what we've got written here. Now the value of the negative comes into it here as well. If we were to think about in terms of the gravitational force, the direction of the radius vector was in one direction, but the actual force is in the opposite direction. So for example, if we take a ball and we move it up the way, so we're moving it away from the planet Earth, the actual force is actually drawing it down the way. So they're in opposite directions. So it's going to be in effect f dot d cos theta, it's the dot product. So it's going to be the cos of 180 degrees, which is -1. So give you a minus sign here. So we can integrate this thing from r to infinity of m mu upon r squared by dr, and that gives us minus mu 1 upon r. And that's really correct because we want the potential energy to be actually a negative value. So it means that if we add both these together, we're going to get our half mv squared minus mu upon r is equal to a constant. And then when we rearrange that, we can get it in terms of v squared. So that means v squared will equal 2 mu upon r plus 2k. Okay, so I've actually missed out that little line there. You could maybe put that in yourself and convince yourself. So you just need to write that a half mv squared minus mu upon r equals k, and then solve for the v squared. So we get this line here. So therefore we can write that in terms of v squared. So we can see our v squared, we can take out the common factor of the u. It'll be 2 upon r plus 2k upon mu. So therefore we can say that the v squared is going to equal the mu times 1 upon r minus 1 upon a, if we term this value a is equal to mu upon 2k. So it means that we can therefore write that v is going to equal the square root of 2 upon r minus 1 upon a to the power of a half. So again, just convince yourself of that. This little term here, the 2 upon r minus 1 upon a to the power of a half, is the thing that really gives us the orbital velocity of something travelling within an elliptic orbit. Now that's what we're really looking for here, this little term here. So just work through the little bit of maths there and transposition and just convince yourself that you get this term here. So the other term we're looking to get is the value of our ds. Now I will leave you to work through the derivation, but I'll give you a hint. Remember, whenever we looked at the geodesics on a sphere and geodesics on a cylinder, we worked out the value of ds in the spherical coordinates. So we're able to say that our ds squared was equal to our r squared plus r squared d theta squared. So we derived that in a previous video. So then what we do is we just take the value of our dr squared down to the other side, and we get our 1 plus r squared d theta dr squared, and then we can take the square root, gives us the power of a half, and then we can take our dr up, which gives us this term here. So these are our two terms, and we can put that back in to our equation for our functional here, which is going to get minimized, so we're just putting it back in to this term here. So putting that back in, we're going to get I is equal to the value mu integral from, we'll do it from 0 to 2 pi, of our value here 2 upon r minus 1 upon a to the power of a half, and our ds is our 1 plus r squared d theta by dr squared to the power of a half by dr. So this is our term here that's going to be getting minimized. So let's have a look and see how we're going to do it. We can see the functional here. Well, it's a function of the independent variable r. Now the only other things up here within this equation here that are functions of r is the value of our theta. So it's d theta by dr, so it's actually theta derivative. So we can see here that in this functional form here, we can simplify the Euler-Lagrange in terms of the theta derivative. So it can be written as partial f by partial theta derivative equals a constant. So there's a bit of physics involved in that, and I've maybe skipped over this bit about the potential energy. I didn't want to get into all the details. If you've not done any physics, you can always send me an email or get in contact if you're unsure about any of this, and we can have a chat through it. As I said, I don't want to get into lots of detail in the physics. I'm really just using the physics in order to give us some examples of how to do the mathematics. So let's continue with this, and we'll work out the value for our functional. So we're looking at our partial f by partial theta derivative equaling a constant. So the first part of it, there's no value of theta, so we just leave that as is, 2 upon r minus 1 upon a to the power of a half. Now the second term does have a factor of theta derivative, so what we do is we differentiate that, so it would be a half of 1 plus r squared theta derivative squared to the minus a half, and then we differentiate what's inside it. So we differentiate that, we get 2r squared theta derivative. And we, in order to make the maths work out for us, we'll say that the constant is equal to the constant to the power of a half. So we can do anything with that constant we want, just to get things into the right format. So that's just got that line there. So we can leave this as is. In this case here, the 2 is going to cancel out with the 2 there, so we're going to be left with our r squared theta derivative upon, and we'll take the minus a half down, so 1 plus r squared theta derivative squared to the power of a half is equal to c to the power of a half. Now, to simplify things out a bit, we'll replace this 2 upon r minus 1 upon a with this term beta. Okay, so now we're simply left with the value of our beta. Now what we'll do is, if we were to square both sides, okay, so if I squared this whole thing here and squared that side, I can get rid of the factors of powers of a half and a half on the bottom line. So we'll be left there, finally we'll be left with our value of b, and then we'll have our r to the 4 and theta derivative squared all upon, now the factor of a half will disappear when we square it, so 1 plus r squared theta derivative squared is equal to, now our c squared will just be our value of c. So we can take this term up here, that'll give us this line here, we can multiply out by c, we can take the value of this c r squared theta derivative squared over the other side. We've done that here, is equal to a constant. We can take out the common factor of theta derivative squared, it gives us this here, equals c. So a theta derivative squared will be this value c upon beta r to the 4 minus r squared c. So then finally we can put our value for beta back in, which will give us c upon 2 to the r minus 1 upon a, r to the 4 minus r squared c. So we can see here then that theta derivative squared, well what we'll do is we'll multiply the top and bottom line by c, top and bottom line, sorry, by a, will give us the value ac, and that will give us, if we multiply that out and multiply by a, will give us a 2ar cubed minus r to the 4 minus r squared ac, which gives us this line here whenever we divide throughout by the a. So we get our r squared times 2ar minus r squared minus ac. So it means that if we take the square root of both sides now, we're left with our theta derivative equals this term here, it's the square root of this term here. So finally what we're going to be doing is, and the reason for knocking it into this format here, is we're going to use a standard integral. So the standard integral we're going to use this integral from a to b of minus 1 upon root of a squared minus x squared by dx equals inverse cos x upon a. So again, that's a standard integral, and we've seen that before in a couple of other videos, and you can see how there's an awful lot of the mathematics gets repeated in lots of these examples, and we tend to use very similar mathematics. So once you start working through, they seem difficult at first when you first see them, but once you start working through lots of examples, you see the similarities between them and they start becoming a lot easier. So let's continue with this on the next page. So we can use the standard integral from the previous slide along with the substitution u equals c upon r. Now we've used this same substitution in previous videos, and whenever we do this substitution and work out the integral, we get the final equation in this form here. C upon r equals 1 plus 1 minus c upon a to the power of a half times cos theta plus beta. And this value here, 1 minus c upon a to the power of a half, is the eccentricity, and this is the equation of an ellipse. Now the derivation here is a couple of pages long. I didn't want to put it in here. I've put it in to the resources section so you can go and download that as a PDF. Also, the derivation wasn't actually done by me. One of the students, David Siffer, who purchased the course, he worked through that derivation and sent the full derivation off to me. So thank you for that derivation, David. So let's go ahead and we'll have a wee look at this in the Desmos and we'll see how it works. So I have the equation of the ellipse here in the graphical calculator. So you'll see that The eccentricity is given by this factor here, the 1 minus c upon a. Now if I was to make this value a tend towards c, so at the moment that c is equal to 1, so if a was to tend towards 1, then we'd have 1 minus 1, which is 0, that whole thing would be 0, and we would simply have the r would equal the value of c, which in this case would be 1, so it would just tend towards a circle of radius 1, and you can see that here, as the value of a decreases, we get the eccentricity decreases until eventually, when it gets to a value of 1, it just becomes a circle. And of course, whenever the a is less than 1, then we'll have a number here that's going to be head towards 0. So we'll have a number here. If that's less than 1, then this whole thing here is going to be greater than 1. So we'd have 1 minus a larger number. So that would be the square root of a negative number, which would get into complex numbers. So it wouldn't be defined for any values wherever the a is less than the value of c. Okay, so the value of a must be positive. So there it's heading off, and you can see that the eccentricity increases, it becomes more elliptical. Now the other term here, the value of beta, just generalizes this curve, and it rotates it round another axis. So the angle theta here would be the angle from some central point here to the actual curve on the actual ellipse. But then let's say for example it was from this point here, so it would be this angle here over theta. But we can rotate the whole thing round by a factor of beta, and you can see the whole thing getting rotated round by beta there. Okay, so that then gives us our equation of our ellipse, and that's us derived it. So it's a kind of general equation of an ellipse that we've derived via the calculus of variations. So that's all there is for this video. I'll get you on the next video. Goodbye.